I guess the dessert is too nice. All right, let's get started. We have pretty full schedule. 5 talks in a little bit of an hour, so 20 minutes each. Okay. So my name is Dr. Yilan Zheng. I'm the session chair. I'm from UAB. The first talk about hardening signature scheme via drive and de-randomize stronger security proof for EDDSA by Mihi Beller, Hannah Davis, Ziding D. And I guess speaker will be Hannah.
Thank you. My name is Hannah Davis. I'm from UC San Diego.
Yep.
Okay. Cool. So I guess I'll start back with a digital signature has 3 algorithms, and I have just messed this up more, so I guess I'm going to pull back. Digital signature has 3 algorithms: one to generate a public-private key pair, one to take a secret key and a message and generate a signature, and one that takes that signature and a public key and verifies whether or not the signature is valid. Our security goal for a digital signature is going to be existential unforgeability, which means essentially that an adversary given access to a signing oracle should not be able to produce a valid signature on a message that it hasn't already gotten a signature on from that signing oracle. So the eventual goal of this talk is going to be to give a security analysis of the EDDSA signature scheme. But first I want to talk about Schnorr signatures, which are built from a prime order group in which the discrete log problem is assumed to be hard, and a hash function, which we'll call H. A Schnorr secret key is essentially just a random element of the integers modulo the group order. And its public key is the group element whose discrete log is the secret key. To sign a message, we pick a random group element, hash it together with the public key and the message, and then we use that the discrete log of our random element to mask the product of the secret key and the hash. To verify the scheme, we then multiply the hash by the secret key and mask it with the random group element. We compute that value 2 different ways from the signature and check that they both match. Schnorr signatures have been pretty prominent in the literature because they're simple, they're efficient, they're relatively straightforward for a discrete log-based scheme, and they're reducible to the discrete logarithm problem, as long as you're willing to assume that the hash function H can be modeled as a random oracle, basically a public random function. In addition to the initial Schnorr security proof, there have been a number of more recent results that have improved the bounds and basically validated Schnorr for shorter and shorter parameters. The downside of Schnorr is that it's susceptible to a randomness reuse attack. So if you sign 2 different messages using the same random group element, any attacker who gets a hold of those 2 signatures will be able to extract the secret key. And that's where EDDSA comes in. EDDSA was developed in 2015, essentially as a set of tweaks to the Schnorr signature scheme that make it more secure and more efficient at the same time. And we're going to address these tweaks one by one. So the first tweak is changing the group basically to one with a faster implementation called a twisted Edwards curve. And the main change we need to worry about is that a twisted Edwards curve is not a prime order group. Instead, its order is a prime multiplied by a small power of 2 called the cofactor. And this changes our verification algorithm just a little bit, because verification might now receive a signature where the group element isn't in the prime order subgroup, it's in the group as a whole. So this gives us two different variants of verification depending on how we want to handle that. We can either check equality based only on the part of the group element in the prime order subgroup, or we can check equality as the whole. And we call these two variants permissive verification and strict verification. Our analysis works on both of them, but we have to pick one. So for the rest of this talk, I'll be working with permissive verification. The second tweak that EDDSA does is it handles the possibility that the secret key is generated by a biased random number generator by expanding the secret key using the same hash function used in Schnorr. And we also perform a little bit of formatting on that secret key called clamping. In this case, what we're doing is we're setting the high order bit of the secret key to 1 and the 3 low order bits to 0. And the final thing, the thing that actually fixes the randomness reuse attack, is we de-randomize the signing algorithm and make it deterministic. This is a standard technique, effectively using a PRF to derive pseudo-random coins from the message and an extra part of this expanded secret key. Since we're using the hash function everywhere, I should mention that this hash function is given two specific options in different instantiations of EDDSA. For the lower security ED19, the hash function we're looking at is SHA-512, and for the higher security, the hash function is shake. And I've mentioned in all of the Schnorr analyses, we assume that this hash function is a random oracle. And in the one proof of security for EDDSA, which we'll get to shortly, this assumption is the same. It's assumed to be a random oracle. So we want to make sure that that's a reasonable assumption to be using here. So let's look a little bit more closely at SHA-512 and shake. They're both built by iterating a smaller primitive. For SHA-512, it's a compression function. For shake, it's a permutation. And obviously, they don't look random. They're fixed known functions. We can compute their values. They're not random. In order to model them as a random oracle, what we want is we want for them to look like a random oracle when their ideal primitives are assumed, when their underlying primitives are assumed to be ideal or assumed to be random themselves. And what this will give us is it will help us ensure that the structure of SHA-512, this iterative structure, isn't going to become a problem when we plug it into something that's assuming it's a random oracle. So we can evaluate the structure in the indifferentiability framework, which was first designed for checking whether hash functions can be safely modeled as random oracles. There are existing results for both of these functions, and what they say essentially is shake can be safely modeled as a random oracle, but SHA-512 can't. And that's because of the length extension attack, which is pretty well known and applies to all Merkle-Domgaard hashes, of which SHA-512 is one. Effectively, what a length extension attack is an attacker who has access to the compression function can predict certain outputs of SHA-512 without having to compute the entire construction. This doesn't make EDDSA insecure. The designers of EDDSA knew about the length extension attack. They took it into account, but it doesn't show up in any of the formal analysis. And it does mean that we can't actually assume that SHA-512 can be modeled as a random oracle. So coming back to EDDSA, there's one security proof for EDDSA by Brendel et al. And this security proof essentially models the original Schnorr proofs, where it breaks down the Fiat-Shamir structure of the Schnorr signature scheme. And like those original proofs, it's not quite tight. It has a quadratic loss that comes from the original forking them. And it also is making the same assumption that the hash function, whether it's SHA-512 or shake, is going to be a random oracle. So what we did, what our goal was to give a new security proof of EDDSA that doesn't go all the way back to the discrete log problem. It just reduces directly to the security of a Schnorr signature scheme. And what that gives us is we don't have, it's first of all a much simpler proof. And second of all, it means that we can rely on all these more recent proofs for Schnorr that have tighter bounds that validate shorter parameters. And we can just plug those into our approach in a modular way. The other, so I will quickly point out as an example what this gives us for concrete bounds. If we have a sample attacker with a 2 to the 70 runtime bound and 2 to the 60 query bound, then against ED25519, we can save 10 bits or so just by using tighter bounds for Schnorr. And if we're willing to change assumptions, like some of the much more recent analyses of Schnorr do, then we can save up to 100 bits of security. So we're able to validate much, much larger parameters and get much better guarantees for this, for the parameters that are actually used in practice. The other thing that our proof does is instead of assuming that SHA-512 is a random oracle, we assume that its compression function is a random oracle, which means that we can explicitly take into account things like length extension attacks. We can explicitly validate that choice of hash function. And we aren't making this, we don't have this problem. And in addition, while we were doing this proof, we also came up with some handy intermediate results that we think have a little bit of independent interest. The first is derived then de-randomized, which is a generic signature scheme that captures these tweaks that EDDSA is making to Schnorr and makes them generic so that they can be applied to any scheme as a de-randomization strategy. And the nice thing is that our validation of the derived and de-randomized transform happens in the standard model. So we don't need to make any random oracle assumptions at all there, and we can work in any model generically. The second contribution we have here is a closer analysis of a class of MD-based hash functions that both captures the way that EDDSA uses SHA-512 and validates it, but also improves on prior results for existing hash functions like ChopMD, which is used to build SHA-384 and might be useful in other schemes as well. So this is our transform, derived then de-randomized. And what it does is it takes in a randomized digital signature scheme, a PRF, a PRG, and a clamping function, and it builds a deterministic signature scheme. And one thing, and I won't go into details on the construction, but essentially it's doing the same thing that EDDSA does. It's expanding the secret key, it's clamping, it's de-randomizing. The only thing that it doesn't do is change the underlying group. One interesting thing about the DTD transform is that, first of all, the reduction is completely tight. We're only losing a constant factor based on how much of the secret key we lose during the clamping process. And the other interesting thing is we're not assuming independence for any of the components. So we do allow the digital signature scheme and the PRF and the PRG all to depend on the same underlying components, which is important in, for example, EDDSA when we're building them all from SHA-512 and its underlying compression function, which would be our random oracle here. So I'll move through this pretty quickly for time's sake, but our proof for the derived then de-randomized transform is fairly straightforward. We reverse the transform step by step, relying on first our PRF or PRG property to undo the key expansion, then our PRF property to undo the de-randomization, and finally we stop clamping and just lose a factor based on the probability that a random key will be clamped in the first place. So the last thing I want to talk about is that in order to use this generic derived then de-randomized transform on EDDSA, we need to make the appropriate choices for each of the components. So our digital signature scheme is going to be Schnorr. Our clamping function is this function I discussed before where we set the higher order bit and wipe the low order bits. But our remaining components are a little bit more complicated because they're all based on a single hash function or random oracle. Depending which model you're in. So we have a pseudorandom function, a pseudorandom generator, and a random oracle. And we want to make sure that we can get all of these things, even if our hash is an empty hash and has that underlying structure, provided we can assume the compression function is ideal. For the pseudorandom function, this is pretty straightforward because EDDSA is using the AMAC construction, which has already been proved secure with an empty hash. For the pseudorandom generator, we show this directly, but it's pretty trivial because the generator is just calling the underlying compression function exactly once and returning its output directly. The interesting point is showing that our hash function behaves as a random oracle when we reduce its output modulo P, and we prove this directly in the indifferentiability framework. So I have very little time, but if you're familiar with indifferentiability, the way what we have is we have a real world where there's our construction. So in this case, C would be SHA-512, and our compression function, which is idealized as a random oracle. And in the ideal world, we want to keep the same interface, but we want to replace the hash function with a random oracle. And we need something to replace the compression function on the right. And that's going to be a simulator. So the simulator that we use takes, I'm going to skip through this, but basically say we're not just proving indifferentiability for Merkle-Damgard reduced modulo prime, and we're also not just doing it for Merkle-Damgard reduced modulo prime and the CHOP-MD construction, which effectively reduces by a power of 2. We're doing it for any transform that truncates the output of a Merkle-Damgard hash in a way that can be sampled in reverse. And the details on that are in the paper. Okay, and with my last couple minutes, I'm just going to say we think that our proof has a little bit of independent interest, because while we were looking at the CHOP-MD proof, we found a minor bug. And the way that that works is there's a simulator that is supposed to simulate a random compression function. And that works by building a tree where each edge in the tree represents one compression function execution, and a path through the tree represents one full evaluation of Merkle-Damgard on a message. And usually proofs add extra nodes to this tree over the course of the proof to represent full hash function queries that are made by the adversary. But since these nodes change the simulator state, they can change its responses slightly, and that can be detectable in certain somewhat unlikely situations. So our simulator avoids this by constructing 2 trees, responding to adversarial queries with one and using the other internally and bounding the probability that they diverge. And that's what I've got. Thank you for your time.
Yeah, we do have question for a couple of questions, time for questions. Yes.
Sorry if I missed it, but how do you actually define a clamping function?
So a clamping function is just a function that maps the set of all possible secret keys to a subset of itself. So we format the secret keys and project them into a smaller set. And the only property that we require of this clamping function is that the subset of clamped keys is at least a large fraction of the entire set. So we're not losing too much entropy in the secret keys when we clamp.
Questions? No, well, thank you very much. The next talk by Anna Lisyanskaya about security analysis of LSA BSSA.
Put it on your. Put it in the pocket or somewhere where you can.
Oh, okay. I do have a pocket.
Let's try this. Okay. Hi, everyone. My name is Anna Lishansky, and I'm going to be talking about the security analysis of RSA BSSA. Okay. Okay, I'm just going to talk like this. Oh, it wasn't me. Oh, okay, good. Okay. So what's RSA BSSA? We'll get to that. But now let's talk about blind signatures. So what are blind signatures? This is what this talk is about. Thanks to the previous speaker, we know exactly what a regular signature scheme is. A blind signature is a signature scheme that has a key generation algorithm, just like a regular signature scheme, verification algorithm, just like a regular signature scheme. But signing is now a secure protocol between a signer and a signature recipient, where the recipient just knows the public key and the message he wants signed. The signer knows the secret key. The wheels turn. The user's output is the signature on the message, and the signer learns nothing other than he just successfully ran a signing protocol. And the blindness means that the signer learns nothing. So that's what blind signatures are. Why is this a primitive we've been studying for the last 40 years? It was proposed by David Chaum in order to digitally represent money in a way that's privacy preserving. So that was 40 years ago. So why now? So blind signatures are suddenly important. Why are they suddenly important? Well, let's say that you want to prove that you're not a robot, not a troll, not a bot. And so you're asked to solve a CAPTCHA. If you had to solve CAPTCHA for every single site you visit, that's extremely onerous. So it would be nice if you could just solve a CAPTCHA once, get some kind of digital tokens that you can then go and spend in a way that's not even linkable to your CAPTCHAs or to each other. So that's one current use of blind signatures. And that one is maybe a little hypothetical, but actually online advertising platforms want to use them for accounting purposes. This is kind of part of this big plan to phase out third-party cookies. Don't ask me about that too much. Google uses blind signatures as tokens in their VPN. And so this is when, if you're using Google One VPN, this is what's happening under the hood, is a blind signature. So when you log into the VPN, Google doesn't, the server doesn't know who you are, but you use a blind signature as a token. And Apple's using them to let you browse the web anonymously using this iCloud private relay. So suddenly blind signatures are being used. And our focus is a specific blind signature scheme called RSA BSSA. BSSA stands for Blind Signature Scheme with Appendix. And it's an IETF. At this point, it's still a draft, but it's about to be standardized by Dennis Jacobs and Wood. So this is the Apple side of that big picture that I just showed. So this is the first proposal for a standardized blind signature scheme. The reason that they went with this scheme and not some other scheme is because it builds off of RSA PSS, which is of course part of the PKC as #1 standard. So it's everywhere. People already have libraries for at least the key generation and verification part. So it's just a signing protocol that they had to introduce. And it's used in Apple's private relay. Okay, so that's our focus, is this particular blind signature scheme. So here's a summary of our results. So first of all, the good news is that RSA BSSA is strongly one more enforceable, and that's the gold standard notion of security for enforceability for blind signatures, and I'll get into it in a moment. And it is enforceable under this one more RSA assumption that 20 years ago, more than 20 years ago, when it was introduced, maybe you would have said one more RSA, what's this? But by now it is a relatively established assumption in the random oracle model. And of course, right now, one question is why standardize something that's not quantum resistant? Well, the enforceability doesn't hold in the quantum world, of course, because it's RSA is not secure with quantum computers. But this only affects enforceability. So, at the time when you're using your tokens, which is today, they are unforgeable and we can go on using them, but your privacy is everlasting, even if quantum computers show up. Okay, so that's unforgeability. But what about blindness? So the first draft of this IETF standard, actually, I don't know that it isn't blind, but the proof of security hit a snag, and I'll tell you why. But you can fix it with minor modifications. And the interesting thing is that the alternative, the one that Google uses, the blind version of RSA FDH, is actually doesn't satisfy the definition, the modern definition of blindness either. But they both satisfy a weaker notion of this blind token, which we've defined, and it turns out that it's good enough for the applications where they're used. All right, so that's a summary of the results. Now let's jump into the details. Okay, so what's the definition of a blind signature? So as I said, you have a key generation, a signing protocol, and a verification algorithm. Key generation verification, same as in a regular signature. The signing protocol, here we will focus on just the 2-round structure of the signing protocol. And if we're willing to just only consider 2 rounds, then the definition looks like this. It's a protocol that consists of 3 algorithms. The blind algorithm, where the user generates this message to the signer. The BSIG algorithm, where the signer actually produces kind of an initial something that looks like a signature. And then the finalized algorithm, where the user extracts the signature from the signer's answer. Okay, and we want this to satisfy correctness, unforgeability, and blindness. Correctness, always the same. You know, if everybody follows the protocol, everything works out. Unforgeability is one more unforgeability. What does that mean? It means that if you have a malicious user who gets a public key of the signer and gets to interact with the signer, ask him to issue blind signatures. So send him blinded messages and get a response. Send him another blind message and get a response, and do it L times. And then if he outputs, then this malicious user outputs all the message signature pairs. This user wins the one more unforgeability game if he manages to output more message signature pairs than the queries he's made to the signer, then he is allowed to. So it's called strong one more unforgeability if all of the messages are distinct. And what about many round protocols? Well, then if you wanted to define them, there'd be like a question of, okay, there's sequential security for these many round protocols, or you can maybe want to care about concurrent strong one more unforgeability. And the nice thing about only caring about this 2-round structure is that if your protocol has only 2 rounds, then sequential implies concurrent, and you don't have to worry about these subtleties, which is suddenly very important because 2 years ago there was an attack. They showed it turns out that it's very subtle. So better to just deal with the 2-round structure and not worry about it. Okay, so that's unforgeability. And blindness formally means, and I'm going to go super fast, is that if you have an honest user who cares about his privacy, doesn't want the malicious signer to know which message the user once signed, even though the signer says, here's my public key, and here are 2 messages that I want you to obtain signatures of, when the user gets them signed in random order, so he sends his blinded messages, he gets back the blinded signatures, then he unblinds them and sends them in the same order as the messages he received. The malicious signer cannot figure out in what order the signatures happen. So that's blindness. Okay, so I just gave you these definitions. These definitions are actually standard, and it took the community many years to settle on these definitions being correct. And it is kind of important. So the one more unforgeability definition was, the original version was given in '96 by Poichwell and Stern, and then this strong unforgeability, and the reason it's preferable, was not given until 2012. And for blindness, the first try was in '97 by Jules Luby and Ostrovsky, and then the improved definition is to account for the fact that the public key might be chosen maliciously by the signer, and you still want blindness to hold. And in that intervening time between 97 and 06 is when the original blind FDH RSA was published. So it had a proof of security, proof of blindness under the original definition that didn't account for the adversarial signer, which is why I said, oh, but it doesn't. One of our results, and this is all I'm going to say about it, is that if blind FDH RSA isn't blind under this more modern definition. Okay, so that's definitions. Now our results. So as I said, what does this RSA results say about RSA BSSA? So what does it look like? So RSA BSSA, the key generation is just an RSA key pair and 3 hash functions, which we're going to model as random oracles in the analysis. The signing protocol I'll show you in a moment. The verification, just this, you verify use the same way as RSA PSS, which roughly means that you take the signature, you raise it to your exponent E, and then you do this PSS decoding. So for now, this looks like nonsense because nobody remembers PSS off the top of their head, but I'll get to it. Okay, so what does the signing protocol look like? Pretty much what you would expect. The first thing the user does when he wants to blind is he PSS encodes his message, and then he gets this EM, which is called encoded message. That's a PSS notation. Take this encoded message, blind it by multiplying it with a random R raised to the E. So now it's a random element of the group Z and star, and send that to the signer. And then the signer computes the ETH root of that, so raises that to the D, sends it back, and then you compute the signature by unblinding. So the PSS encoding is the part that I haven't told you yet, exactly how it works. Okay, so that's a signing protocol. So this is very reminiscent of Cham's original blind signature scheme, except it's PSS encoding as opposed to any other encoding of the message. Okay, so here's a theorem. If the one more RSA assumption holds, then RSA BSSA is strongly one more unforgeable in the random oracle model. So this proposal, this IATF draft proposal, has the unforgeability properties that you want. Okay, and how do we prove this theorem? This is going to be very quick proof by picture. So we want to construct a reduction that solves one more RSA. So it has a one more RSA challenger. It gets an RSA public key. It fires up the adversary who's trying to break RSA BSSA, gives it the same public key. Now it needs to answer the adversary's queries. When the adversary sends it a blinded message, it just forwards it to the one more RSA challenger and gets the answer. So those are the easy queries to answer. And I also need to tell you how to answer the 3 types of random oracle queries. There's the one where you just hash, you have a message that's just like arbitrary length, long text, whatever, and you want to hash it down to a short string. So you just do that random oracle yourself, just respond with a random value. When it comes to hashing, so I'll show you how that works as part of this PSS encoding, hashing some specific things that are called capital M's. That's when you ask your one more RSA challenger to give you a challenge. Then he produces a challenge, and from that challenge, you compute the answers to these types of random oracles. And then in the end, when you output signatures, we want those signatures to somehow be solutions to these challenges. So what does that mean? It means that they are the ETH roots of the challenge values, YIs. Okay, so that's what we want. So we want a signature that the adversary produces at the end to be an ETH root of one of the challenges. And we want him to produce L plus one of them, where L is the number of the questions that we asked one more RSA challenger. And so what does that mean? It means that we want this, if it's a valid signature, we want the YI to decode to the message I. So it means we need to program the random oracle for all of this to work out. So how do we do that? That's when we actually need to look at how this PSS encoding works. So the way the PSS encoding works is you take a message, you hash it using hash star. You add some salt to it because PSS stands for probabilistic signature scheme. So that's where the probabilistic part comes in. Then you pad it with some deterministic padding. package it together, then you hash it together, you get some value H, then you take that H, you run it through some math generating function that takes a little bit of randomness, which is H, and expands it to some long pseudorandom string. You XOR that with salt with some other padding, and then that's your masked salt. DB means data block, but it's really the mask of your masked salt. And then you stick that H in, and then there's just like some other, a few bytes, BC, 2 bytes. And then that is your encoded message. So that's how PSS encoding works. And then the PSS decoding works in the opposite direction. So you kind of go back, and then you check that this M that you get hashes to the right H. So in order to program this random oracle, what we need to do is we need to make sure that this M, this is the MI that's being hashed there, that it's of this form. If it's of another form, just respond randomly. And then we want to make sure that the resulting encoding corresponds to this M. And this is what the resulting encoding is going to look like, this YI. Think of YI as the encoding. So in order to make sure that we program it correctly, we take this this H from this challenge YI and make sure that the math generating function, when you feed it the H, produces the correct salt that came from that M. So this is where the salt came from. So you program, that means that you need to program the math generation function this way. And then the next thing you need to program is you need to program the H. So you need to make sure that H, that this MI actually hashes to the H that comes from your challenge Y. And after you've done that, there's 5 more pages of analysis gives you the theorem. All right, so that's the first theorem. But blindness is a different story. So blindness is where there's a surprise, where actually I couldn't show blindness. Well, first of all, the easy part is that if E is relatively prime to phi of n, then blindness holds. And that's because in that case, this blinded message is just a random element of the n star. So that's easy to see why. But that's not good enough, because maybe the adversary prepared the public key in such a way that E is not relatively prime to phi of n. So in that case, so one thing that he could do is he could make n the product of T primes such that E divides each and every phi of pi for each. Anyway, you know what I mean. So that E is a multiple of pi minus 1 for each of them. So in that case, information theoretically, this blinded message actually reveals a lot of information about the original EM. So you blind this EM by multiplying it with R to the E for a random R, but it's still, if you think of it as like equivalence classes, it still lives in the same equivalence class modulo each P as the original EM. So those bits, I mean, they're leaked information theoretically. We don't know if there's any way for this adversary to actually recover them if he prepared n this way. I mean, no, he can recover them, sorry, but if you can use them somehow. But what's the worst case? So the worst case is here is our EM. It is, of course, blinded, but it's leaking. So it's leaking some bits. The worst case is that these are the bits that are being leaked, that live somewhere here. And if these are the bits that are being leaked, then we have the H. We can feed it through the math generation function. Now by we, I mean the adversary, can feed it through this MGF and recover the salt. Why? Because he has these bits, these black bits in the clear, and then when he XORs them with this MGF of H, he gets the salt. And if he has the salt, then he can, and he wants to guess, is the message being signed message 0? And he takes message 0, hashes it to this M hash, sticks the salt that gets M, checks, does this M hash to H? And if it does, then it's not blind. Okay, so therefore this version has no blindness, and we want provable blindness, so we can modify it. The 2 ways of modifying it, both very straightforward. Either you just add some additional salt to the message, And then the adversary cannot recover this because there's an additional salt over there that he doesn't know. Or you just make sure that your public key has some proof that E is relatively prime to phi of n. And this can be done using known techniques. And I'm going to skip this new notion of blind token because I'm out of time. And this is just a summary of the results again, is that RSA, BSSA is strongly one more enforceable. It doesn't, the new version satisfies blindness. The original version satisfies a weaker notion that is good enough for the application. And there's an open problem that I guess I should have mentioned when I was presenting, that whether this original version actually is blind is an interesting open problem. That's it.
We've run out of time, unfortunately, for questions, so I encourage you to
Sorry.
later. So the next talk. Next talk is by Jinar. Vicindu Bota area theory. And the title is about extendable threshold signature with enhanced anonymity. Speaker is going to be Jinar.
I really don't remember. It's 30. Yes. Okay, perfect. Okay, so this is joint work with Vincenzo Botta and Dario Fiore. Today I'll talk about extendable threshold ring signature with enhanced anonymity. So extendable threshold ring signature were introduced at last year PKC by Aragna, Landersen, Itulescu, Pagnin, and Yakubov. And I introduced this primitive throughout an example. So basically, imagine that we have a user A that wants to start a public petition, and he also knows the public key of user B and user C. User A would encode the petition in this message gem, and then he would run a signing algorithm on input his secret key, the message, and all the public keys that he knows. And this will give us output 1 out of 3 signature that basically certifies that the message gem was signed either by user A, user B, or user C, but without disclosing the concrete identity of the signer. And then user A can start the petition by posting the message and the signature on a public bulletin board that everybody can see. And now imagine that, for example, user C also know the public key of another user, user D. She can run an extend algorithm that will take as input this previous signature on the bulletin board and this additional public key of user D. And this will produce a 1 out of 4 signature that now hides the identity between 4 signers. And imagine that user C wants to endorse the proposal as well. She can run a join algorithm on input the previous signature and their secret key, and this will produce a 2 out of 4 signature that now certifies that the number of signers is 2. And then she can publish this signature as well. And the petition can go on with people joining with extension and join procedures as I shown before. So what was the anonymity notion that was considered in the previous work? So we have an adversary and a challenger, and the adversary will query the challenger with 2 sequences. So let's take a look at these 2 sequences. So basically, these 2 sequences are such that they ask for an operation of the signature scheme at each step. So for example, sequence S0 first ask for a signature with message gem on public keys PKA and PKB, and then and requires it to be done with the secret key of A. Then the second step is an extension query with the public key of C, and then a join query with the secret key of B. And on the other end, in order for the adversary to be admissible, this sequence S1 must be compatible with S0. So by compatible, I mean that at each step of the sequence, the kind of queries are of the same type and the public inputs are the same. And then the challenger will pick a random bit and then will compute a signature according to the sequence SB. And then very crucially here, what the challenger will send to the adversary is the signature that results from the last step. So in this case, it will be a 2 out of 3 signature. And then the adversary will have to guess what was the bit that the challenger picked. And then we say that the scheme is anonymous if the adversary doesn't get lucky in guessing more than guessing at random. And yeah, so if you take a look at the application scenario that I've shown before, this definition doesn't fit with the application scenario because as you may see, the adversary and everybody will see a sequence of signature. So actually, that's the modification that we make to the definition. We allow the adversary to see more signature. So all the signature that result from each step of the sequence. And actually, when you look at the instantiation of the previous year paper, it turns out that the most efficient instantiation that they had doesn't satisfy our strong anonymity notion. And indeed, there is a very easy attack to break it according to our notion. And there is also another instantiation that it's way less efficient, but satisfies our strong anonymity definition. But nevertheless, our instantiation overperforms the previous work, both in terms of signature size and time complexity of all the operation that you can make in the signature scheme. So here, little n is the size of the ring, K is the current threshold, and capital N is an upper bound on the size of the ring that has to be fixed from the very beginning, so may be much bigger than little n. So now I want to show the techniques that we use. So first I introduce K out of n Lewis, so non-interactive witness indistinguishable proofs, where you have a trusted party that publishes a common random string, and then you have a prover and a verifier. They both get in input n instances, which may or may not be in an MP language. And then the prover gets as additional input K witnesses that certifies that K different instance and witness pairs are in the NP relation. And then the prover will just send one message to the verifier that is a proof, and the verifier will either accept or reject. Aside from soundness guarantees that this proof system has to satisfy, here we are more interested in witness indistinguishability, meaning that even if the verifier picks the witness to be used, he actually can distinguish a proof done with a certain witness or a proof done with another witness. And yeah, so now I'll show that if you can sort of change the NIWI to be extendable in the same way of the extendable threshold ring signature, you can get an extendable threshold ring signature scheme very easily. So what do I mean by this simple notion of extendable NIWI is this? So for example, a first prover using one witness will produce a 1 out of n1 proof, and then this proof will need to be updatable by many different provers using only one witness. So for example, prover P2 will produce a 2 out of n1 plus n2 using just one additional witness, and so on and so forth up to prover K. And if we have this, we can get an extendable threshold ring signature very easily. So we set the public key of the scheme to be an instance, and the secret key of the signature scheme to be the witness for that instance. And then to get the CRS, we hash the message. And if the CRS is uniformly random, and we're in the random oracle model, this is fine. And then basically we can now map an algorithm of the signature scheme to an algorithm of the extendable NIWI. So to sign, we will run a proof with the CRS derived from the message, for example, and so on. But however, such a simple notion, as I shown, can't exist. It's very easy to see why. If you, for example, produce a 1 out of 3 proof using the witness for instance 1, that's why I colored it in red here. And then, for example, you run a join operation with a witness for instance 2, you'll get a 2 out of 3 proof. But what happens if you run a join operation on the first proof, but using again a witness for x1? You would get a 1 out of 3 proof again, or this should fail, because otherwise you don't have any soundness proof of knowledge guarantee. So basically what I've shown is an algorithm to distinguish what witness was used in the proofs. So this will not be witness indistinguishable. So we have to tweak the definitions a little bit. So we introduce the notion of auxiliary values together with the proof. So for each instance, the prover will produce an auxiliary value, and these auxiliary values have a color. So basically they are red whether if a witness for that instance was used to make the proof, or they're green otherwise. And now when you run an extend procedure, you will produce an additional auxiliary value for the instance that you just added to the proof. And then when you run the join procedure, you will consume one green auxiliary value, and you will use the witness for that distance to produce a 2 out of 4 proof in this case. And the witness indistinguishability notion is like this. The adversary will sample a statement and 2 possible witness. And then the challenger, basically, we can imagine that computes both proofs with both witnesses, and then picks a random bit to select which proof to send to the adversary. And now, together with the proof, it will send a subset of all the auxiliary value. And the auxiliary value that are being sent are not all the auxiliary value, but in this case are the auxiliary value number 1 and 2, that basically are the auxiliary value with the same color. So intuitively, this auxiliary value just should tell if a witness was used or not. So they shouldn't tell anymore. So in this case, this shouldn't help the adversary. And now, of course, the adversary has to guess the bit. So now, if we add the public key encryption, it's very easy to get an extendable threshold ring signature for this from this extendable NIWI. We just increment the public key with a public key of a public key encryption scheme. And then, as before, first we hash the message to get the CRS, and then to sign, we make a proof. And additionally, we encrypt each of these auxiliary value with the public key related to the corresponding user and to the corresponding instance. And then as output, we will give the proof and the encrypted auxiliary values. And if we want to run a join procedure, for example, with the secret key of user 3 can, using his own decryption key, take the auxiliary value. And then as soon as he has this auxiliary value, he can run the join procedure with the extendable NIWI. And this will give us output 2 out of 3 proof after we also re-encrypt the auxiliary value and we give them in output. So why this extendable threshold ring signature is strongly anonymous? At a very high level in the proof, you will have an hybrid in which you want to move from one sequence to another. And basically, you want to use witness indistinguishability in this hybrid. So here it seems fine. It doesn't seem that we need this extended notion with the auxiliary value, but also the definition of anonymity for the signature scheme allows for some corruption. And the corruption that are allowed are corruptions of non-signing user. So in this case, in both sequences, the non-signing user, we have an auxiliary value of the same color. So this would allow at each step of the sequence to reduce to this extendable witness indistinguishability. So now, at the end of my talk, I want to show a little bit how do we get the technique that we use to get the extendable NIWI. We use Grotz-I proofs. In Grotz-I proof, the statement is an equation with several unknowns, and a witness is a satisfying assignment for that equation. And the proof is made of 2 parts. First, you have to commit to all the assignment, and then after the prover has committed to all these assignments, he will run a proof algorithm that on input the equation, the commitments, and the commitment randomnesses will output some proof elements, and the proof is made of the proof elements, pi, and commitments. So now I first show how to get k out of n Grotz-I proofs. So let's start from this example of a simple pairing product equation with one unknown next to. We can modify this equation to have 2 new variables, where basically for each element of the group 2, we add a new variable yi, and then we can add other equations of this type. So in this case, we introduce a new variable m, and we prove that m is equal to g to the power of a bit. And then we also add these equations over here that correlate the m, the yi, and the xi. And then now this has given us some degree of freedom, because we can set the bit b to be equal to 0. If we set the bit b to be equal to 0, this will give g to the power of 0. If we plug g to the power of 0 in here, yi, for the properties of pairing, we can set yi to whatever we want. So in particular, we can set yi to be equal to 1. So we are able to satisfy the modified equation with the trivial assignment. But if we set b to 1, we are forced to pick the yi equal to the xi, and this will give the initial equation basically. So to get a k out of n proof, use this fact. You start from n instances. You modify the n instances as I've shown before, and you add an additional equation in which you prove that all the BIs sum to k. So this in turns is this pairing product equation. It's not really important. And now basically the value of the BI is constrained. So we can have at most k BIs that are equal to 1, and we will have n minus k BIs that are equal to 0. So for k times, we will set the bit to be equal to 1, and we will use the original assignment. And for n minus k times, we will set the bit to be 0, and we can use the trivial assignment to satisfy the modified equation. And basically, as a proof, we will have commitment and proof elements for each individual modified equation, and commitment and proof elements for this additional equation over here. Okay, and now basically, if we want to have an extendability property over here, we just need to focus on this equation over here. Basically, this is because if we want to run an extend procedure, this would imply that we need to add another equation and do this modification and run the proof. But this is kind of independent from all the other equations. They're not correlated together. But the only place where this addition of a new equation over here would have impact is in this sum over here. So here in particular, we will need to add another variable bn plus 1. And if we want to run a join procedure, it means that we don't want to use a trivial assignment for equation. Say, for example, in equation 1, we now want to use the actual assignment. We need to modify this equation to be equal to k plus 1, and we will replace basically this proof with a new proof. So how do we do this? Basically, I will be very high level here. I won't go into the detail of the Grotz proofs, but basically, internally, when the Grotz prover makes a proof for this equation, what he will do, for example, imagine that we start with B2 equal to 0. He will do the following. First, he will commit to all the values of the MIs, including the commitment to M2, that is now g to the power of 0, that is 1. And he will have in his hands all these commitments and commitment randomnesses. And when he basically has to generate the proof elements, you can look at it as it's an addition of all this stuff. So this stuff is combined to get these proof elements. And now imagine that you want to get a join procedure. So you want to make this equation, prove that this equation is equal to k plus 1 now. And we change the value of B2 to be equal 1, and therefore M2 will be G. So you will commit to the variable M2 again, creating a new commitment CM2 prime, and with the commitment randomness RM2 prime. And basically now, what we would like to do is to create new proof elements, modifying the old proof elements. So basically what we need to do is to erase some contribution of the old commitment and add the contribution of the new commitment, because everything else is the same. So we want just to change this part. And basically we will achieve this by using as auxiliary value the commitment randomness related to the variable M2. And once we have this, we have both the commitment that is public, this commitment randomness, we can remove it with the inverse of this operation that I denoted with a plus. And then we can add the new commitment and the new randomness to get an updated proof element pi m prime. So to conclude, in this work, we have introduced a stronger notion of anonymity for extendable threshold ring signature. We provide an efficient and strongly anonymous extendable threshold ring signature. And also, kind of interesting, we formalize this new notion of extendable NIWI, which could be used elsewhere maybe. And we propose an instantiation for extendable NIWIs for pairing product equations. Thank you. I'm open to questions.
One question, please. Well, thank you again.
Thank you.
The last talk of the session, tracing a linear space, application to linear homomorphic group signature by Chloe Huband, David Poincheval, and Shabach. I believe Robert is a speaker, right? Yes.
Hello, can you hear me? All right, so hello everyone. My name is Robert and I will be presenting a joint work with Chloé Ebon and David Pongcheval. And in our work, we introduce a new technique that we call tracing of a linear subspace, and we demonstrate how this technique can be used to build a linearly homomorphic group signature scheme. And I will start with a short definition of our security model, followed by a high-level overview of our construction. And at the end of this construction, we will identify like a key technical problem that we need to solve. And fortunately, there is a very simple solution that we will discuss first. And in the end, if time permits, we also look at a more advanced construction that leads to much shorter signatures. And so actually all the technical stuff in the paper is going on in the last bullet there. But yeah, so this talk is in the signature session, so we can just have a look at the application. Yeah, so as the name indicates, a linearly homomorphic group signature consists of, or is a combination of two primitives, a linearly homomorphic signature and a group signature. And so just as a little reminder, a linearly homomorphic signature scheme consists of 4 algorithms. 3 of them are standard: a key generation, assigning, and a verification algorithm. And the message space of such a signature is always a vector space, meaning that the signing algorithm signs vectors in this case. For example, vectors M1, M2, and M3 in the figure there. And the reason why this scheme is called linearly homomorphic is that given signatures for, say, M1, M2, and M3, we can derive signatures for any message M that can be written as a linear combination over M1, M2, and M3. And the important property here is that this derivation needs only the public key, but no knowledge of the secret key. So essentially, everyone can do it. And for this reason, we need to adapt our security notion a bit. Essentially, what we would like to have is existential unforgeability against chosen message attacks. However, we need to exclude some trivial attacks that are induced by this derivation algorithm. So concretely, if an adversary wants to win the security game, then he needs to come up with a signature for a message that does not lie in the space in the span of those messages that were queried to the signing oracle. And the second primitive that we consider is a group signature scheme. And in this case, group does not refer to an algebraic group, but to a group of users, together with some trusted authority that is called the group manager. And so each party has their own secret key. And in addition, there is one public key for the entire group. And so we consider a signature scheme. So of course, every user can sign messages like this. And all these signatures are valid with respect to the same unique public key of the group, meaning that, or the intuition behind that is that all the users can sign on behalf of this group. And regarding security, we have 2 requirements. The first one is called anonymity, and it essentially means that all the signatures look the same and behave in the same way. And so, of course, anonymity is a very desirable property, but it's also like the perfect environment for corruption or malicious behavior in general. And for this reason, one introduces a second security requirement that is called traceability. And this is the point where the group manager enters the stage, because using this special secret key of the group manager, it is possible to revoke anonymity and to identify the creator of a given signature. And the latter process is called opening of a signature. And now the question is, well, what makes the combination of those 2 primitives actually non-trivial? And my intuition on that is that, so on the one hand, we have this group signatures that gives us several users, and all of these users should be able to sign documents. So we have several signatures. And on the other hand, we have this derivation algorithm that should be able to take arbitrary given signatures and to derive new signatures. And in particular, in our setting, this means that the given signatures are signatures produced by different users. So this derivation process can lead to signatures that do not have only one signer, but like several contributors. And of course, this is important for correctness. So this derivation with signatures produced by different users should again lead to a valid signature, but this is also important for anonymity because the given signatures could either be produced by the same user or by different users. Maybe they are freshly generated or they are the result of a previous derivation process. In any case, the output signature of the derivation should follow an indistinguishable distribution. And this fact that signatures can have several contributors is also a challenge for traceability because it's no longer sufficient to find only one signer of a signature, but what we need instead is to identify a subset of users that contains all contributors to a certain signature. And at this point, so it's really important that the group manager actually finds all of the contributors to a signature, because otherwise an adversary simply could mix its own malicious signature with many signatures produced by honest users, and in the end there would be a good probability that the group manager only finds honest users as a contributor, but not the real malicious user or the adversary. So for a meaningful security notion, it's important that the group manager finds all the contributors to a signature. And so before I will be presenting our construction, I would like to recall a framework for group signatures by Bellard, Michancho, and Varenci. I guess my pronunciation was completely odd, but anyway, so their scheme uses 3 ingredients: a traditional signature scheme, a public key encryption scheme, and non-interactive zero-knowledge proofs for NP. And so as I just said, a group consists of a bunch of users and central authority, the group manager, and secret keys of the users consist of a fresh key pair of the traditional signature and a certificate of their identity. This is essentially their identity signed by the key generator. And in addition, we have this secret key for the group manager that is a secret key of the public key encryption scheme. And so now let's assume that, for example, the green user wants to sign a message. For this, she takes her secret signing key and signs this message. And to make the signature traceable, she adds the certificate of her identity. Subsequently, to make the signature anonymous, she encrypts this tuple using the public key that corresponds to the secret key of the group manager. Now we have anonymity and traceability. What is missing is verifiability. And for this, she adds a non-interactive zero-knowledge proof that this ciphertext actually contains what it should. And the second aspect is how to do the openings. I guess it's already clear. So given such a signature, the group manager takes the ciphertext and uses his secret key to decrypt the ciphertext like this. And so this is actually the crucial step, because the group manager is the only one who knows this secret key. So he is the only party that actually can perform this decryption process here. And after the decryption, one simply extracts the identity of the signer. Now, the question is, how can we make the signature or this framework linearly homomorphic? And for the scope of this talk, we will only concentrate on this gray area here. And to make the whole thing linearly homomorphic, I guess it's a good starting point to analyze, well, what happens if you replace all the ingredients by their linearly homomorphic counterpart. So at first, we will use a homomorphic encryption scheme for the public key encryption. In our case, we use Algamal, but I guess other schemes would do as well. The important property that we need is, given several ciphertexts, and if we want to compute a linear combination over the ciphertext, then these linear combinations should essentially be shifted onto the plain text level, meaning that given several ciphertexts and we compute a linear combination, then this should be equal to one ciphertext that encrypts the linear combinations of the plain text. And in our case, these plain texts consist of two components. The first one is a traditional signature scheme, and of course, we will replace it with a linearly homomorphic signature. This allows us to deal with those linear combinations in a very natural way. But the question is how to deal with this part here. In the BMW framework, this is just any encoding of the identity. And so what does this mean in our context? So we use Algamal encryption. Algamal encrypts group elements. So at a very high level, we could say, well, these identities of the users are just a sequence of group elements, aka a vector. So speaking on a very high level, what we have here is we have one vector for each user. And now what happens if we do a signature derivation? For example, here, let's assume that we have a signature produced by user 2 and one by user 3. And then this derived signature does no longer have one of the vectors, v2 or v3, but it will have a new vector u that is a linear combination over v2 and v3, meaning that omega 1 is 0 in this case, because there was no signature of user 1 involved in this derivation process. Phrased the other way around, if we want to open a signature, then we need to take this vector u, and we need to find those indices I where the corresponding coefficient omega I is non-zero, because this means that the vector vi actually contributed something to this vector u, and in turn this corresponds to those users I that contributed a signature to this signature derivation. And a bit more formal, we call this the linear subspace tracing problem, where we are given a basis B consisting of vectors v1, v2 until vn that span some vector space, and we are given a vector u that lies in this vector space, and we would like to find the set of indices I where the corresponding coefficient omega I is non-zero. And the intuition why we call this linear subspace tracing is that so essentially we would like to find the smallest subset X of the basis such that the vector u still lies in the span of the subset. So in some sense, we would like to find the smallest subset subspace of the full vector space V that still contains the vector u. And I guess a few of you may wonder now, well, isn't it a trivial problem? And clearly, yes, it is. For example, we could choose the vector space Cp to the n together with the canonical basis, and on input a vector u with coordinates u1, u2, un. We simply return those indices I where ui is not equal to 0. And the good news here is that this trivial solution, when plugged into the framework from the last slide, will indeed give us a linearly homomorphic group signature. And even better, this trivial solution is essentially optimal. And what I mean by that is, so to have a unique tracing result, we essentially need that for any vector u, the decomposition into a linear combination over the vectors vi should be unique. And so essentially this requires that all the vectors vi are linearly independent. And now if we want to have a scheme for n users, then we need n linearly independent vectors. So of course, they must have dimension at least n. And if we have a look at our trivial solution, then this is exactly what we achieve. We have n linearly independent vectors of dimension n. So in some sense, we cannot do better here. However, this solution is also a bit inefficient because, as I said earlier, these vectors vi must be embedded into the signatures. So at the end of the day, we have a signature that grows linearly with the number of users in our group, which is probably not really what we want. And for this reason, we consider a weaker notion of traceability, where we introduce an upper bound C on the maximum size of collusions that we are able to trace. And so specifically, what we are able to guarantee is that we still never accuse an honest user, regardless of the size of the collusion. However, a correct opening, in the sense of a complete opening, is only guaranteed for collusions of size up to C. If the size of the collusion exceeds this bound C, then it may happen that we do not find all the traitors. And what does that mean for the subspace tracing problem? I guess the main insight here is that this vector U has a very specific form now when writing it as a linear combination over the vectors Vi. Because now we know that there are at most C non-zero coefficients, and correspondingly we can also relax the condition on those vectors Vi. They no longer need to be a basis, meaning they no longer need to be all linearly independent, but what we need is that only linear combinations with up to C non-zero coefficients should be unique. And this is what I mean by C linearly independence here. And it turns out that this is actually a strictly weaker notion, because it allows us to obtain a more efficient scheme. In the end, we are able to present a construction where vectors have length C squared times log n over epsilon, where epsilon is the maximum probability that the tracing will fail. And for large numbers n, where n is the number of users. So for a large number of users, this is significantly better than O of n, what we had for the trivial solution. And yeah, so I guess my time is over, so I will skip the technical part here and instead conclude. So in our work, we define linearly homomorphic group signatures, and it turns out that the combination of signatures created by different users makes both the derivation and the traceability non-trivial. Well, it is also a difficulty for anonymity, but we can solve this by using Al-Gamal, and by adding encryptions of 0, we can re-randomize the whole thing. So the real challenges are derivation and traceability, and using our subspace tracing technique, we are able to get somewhat short signatures. Thank you very much for your attention. And if you're interested, this is the link to our work on ePrint. Thank you.
Hey, we do have time for a couple of questions. Yes.
If a malicious group member wants to sign a message without being traced, then he can collect many existing signatures, do some random linear combination, sign the difference, and the trace function will output himself and all the previous signers, right?
Yeah, this is exactly the aspect that we also discussed with the reviewers. And my intuition on that is that, so I presented a simplified solution or a simpler variant of linearly homomorphic signatures here. What we have in the real world is that we add tags, and signing proceeds with respect to a tag or a label, and we can only derive new signatures if we have labels. And originally, these labels were introduced to have more control over which signatures can be derived. So this was also in the plain linearly homomorphic signature model. We have these labels to control what for which messages we are able to derive signatures. And in some sense, this is exactly the same problem. If we would not have labels there, then we could essentially sign every message after seeing a few signatures. And so correspondingly, we have the same problem for the tracing. So if we do not have labels, then after seeing a few messages or a few signatures, we can essentially produce signatures with a high probability of not being traced. Therefore, we add labels, and these labels give us some control such that then adversary hopefully will not have too many signatures to choose from, such that exactly the scenario that you described should not be possible.
Okay, one more questions? No, well, thank you very much. Well, this concludes this session. Enjoy your coffee break.